This slide pack is all about the properties of amino acids, and some of this is going to be a little bit of a review because I jumped forward a little bit into some properties when telling you about the structure of the amino acids. But again, structure and property and function, these concepts are all tied together. So we're going to press forward and you can read these learning objectives for yourself. So the chemical property of amino acids is conveyed by the side chain R group. And we could say that the identity, right, the identity of the amino acid depends also on that R group. Again, as I mentioned in the previous set of videos, there's more than one way to group the amino acids, and I'm going to be presenting to you what's in your textbook and just giving you a little bit more information about different ways that can be done. Here are the 20 most common proteinogenic amino acids. These are the ones that are built into proteins. Please do review the R group structure here. It is the R group that conveys the chemical property and identity of the amino acid, because everything else that's not highlighted in orange is identical across all of the amino acids. So where we have this portion of the structure here with your alpha carbon and your carboxylic acid group and your amino group, and we got this hydrogen here, this is all the same in all the amino acids. And if you're observant and you like to kind of argue, you could say, yeah, but what about proline? Proline, we still have the alpha carbon, carboxylic acid group, the amino group, and the hydrogen, but here that amino group is now part of this ring structure of the R group. So in this case, we have a secondary amine, and down here, right in our example I circled for you, serine, we have a primary amine. So we're going to just keep chugging forward here. Here are all of your aliphatic, hydrophobic amino acids, and these guys are hydrophobic. They tend to be buried away from solvent water. So if we're talking about forces that help proteins to fold, we're going to be looking at the shielding of these groups from water so that we avoid forcing order in water molecules. And these guys are going to pack in protein interiors, and this is going to be maximize hydrophobic interactions. Okay. Remember, methionine is special because we have a sulfur in that amino acid. These amino acids are shown at pH 7. The ionization states of these amino acids are as shown at pH 7, and that means that our carboxylate group is deprotonated and our amino group is protonated. More about that coming up. We looked at phenylalanine, tyrosine, and tryptophan. So these are the Phe amino acids. These guys like to absorb UV light at 280 nanometers. And these are great. We can rely on this A280 nanometers, or the absorbance of a protein at 280 nanometers to quantitate protein. And you guys are going to get to do that in lab. Isn't this so exciting? It's going to be great. The other thing that you should note about these 3 amino acids is that they are, I'll say, poorly soluble in water. So they would tend to be in proteins oriented away from solvent water for the most part. An important thing to note about the properties of these aromatic amino acids, right, is that we have on serine an alcohol group, and this is commonly phosphorylated proteins that are involved in cell signaling pathways. Okay, next we have the sulfur-containing amino acids, and here we have cysteine and methionine. So methionine is great because methionine is usually the first amino acid built into proteins at the ribosome, and that can be in the form of methionine as you see here, or in the form of formyl methionine or F-met, so formyl methionine, F-met. Just so that you have the complete story about formyl methionine, in formyl methionine we're going to be attaching a formyl group to this nitrogen. So I'm going to show you what that looks like here. We have our nitrogen, and then we're going to have a formyl group here, and then here's our alpha carbon, right, and our COO minus, and then we've got our hydrogen here and everything else down here. So this structure here shows you what this portion of the molecule would look like in F-met for formyl methionine. So we have that formyl group. Here's your formyl group. The formyl group is attached to that nitrogen. Here are our acidic and basic amino acids, and we covered these in the previous slide pack. I summarized them to you as the musical amino acids because they sing to you, DDD and la la la. So the one letter code here for aspartate is D, and the one letter code for glutamate is E. And down here we have lysine, arginine, and histidine. The one letter code for lysine is K, and for arginine it's an R, and histidine is an H. But you know, if we're going to use the DDD la la la, I think of them as LAH. All right, now the functional groups on these acidic amino acids here are carboxylates, and we refer to them as carboxylates because they are deprotonated forms of carboxylic acid. So because they have a pKa in the range of about maybe around a 4, they're going to be deprotonated at physiological pH. So when we say physiologic pH, we mean a pH around 7. Right, and you know the pH of blood is 7.4. On now to the basic amino acids, and they're basic because they have amines in their R side groups, and we have here lysine with our lysine with our epsilon amino group that you see here. And we have arginine with its guanidinium group, is this portion, and histidine with the imidazole. And so we have the imidazole ring here. Now, at physiologic pH of, pH 7, the groups on lysine and arginine are going to have a positive charge. And so these guys will be positively charged on the R group, pH 7. And histidine is a special case, though, I should say. But histidine is a special case. So histidine is a special case because the pKa for the imidazole group on histidine is about a 6. I have to look it up in the table, but it's about a 6. And this means that we're going to have a mixture of protonated, deprotonated forms, pH 7 or pH 7.4, physiologic pH. So histidine is a special case. And if we're going to add hydrogen to this imidazole ring, we would add the hydrogen here, and then we would have a positive charge. Okay, let's go on. Here you see the polar but not ionic, meaning it doesn't, these side groups haven't developed a full positive or negative charge at physiologic pH. And so we've got serine, threonine, and cysteine. And serine, we have an OH group. Threonine, we have an OH group. And we could refer to this as an alcohol group, right? So this is a primary alcohol, this is a secondary alcohol, or we can refer to these as hydroxyl groups. So we can refer to these as alcohols, right? This would be a primary alcohol, this would be a secondary alcohol, or right, we can refer to this as a hydroxyl, this is a hydroxyl, and over here in cysteine we have a sulfhydryl or a thiol, right? Thiol, OL, like an alcohol, THI for sulfur, so this is a thiol. All right, remember this for future use: sty, serine, threonine, and tyrosine. These are the OH containing R group amino acids which get very commonly phosphorylated in cell signaling pathways. And to add to that list, we also have histidine, which is sometimes phosphorylated. At the bottom you see the amide containing amino acids, and this would be asparagine, right, for N, right, as our one-letter code, and glutamine, glutamink, right, glutamink, which is a Q in our one-letter code system. And these guys tend to be polar, but not ionized. And so you could see here that we have a polar covalent bond between the nitrogen and the carbon. So we're going to be having polar covalent bond in this direction. And we also have the carbon bonded to the oxygen in this direction, right? So anyway, we have the ability to support hydrogen bonds here, as we do up here as well.